Hello, I'm going to be presenting a tutorial on G3d, which is a GUI for running the C3d code. What you're looking at here is not actually the GUI, this is ParaView, which is a recommended program for viewing the results. So rather than starting out with the GUI, I'm going to show you the results in order to demonstrate what problem we're going to be running. So let me switch to some of these things. What we've got here is a tall stack, 25 meters high, ejecting ethylene gas, and it's combusting. And the objective of this tutorial is to predict the radiative heat flux on the ground and on the stack as a function of time. So with that, I'd like to actually show you what the result looks like. This was a 10-second run, and it predicted the heat flux, which varies in time, and you can see that on the ground here. There's the flame at the top of the stack burning. This stack is 25 meters high. The domain here is 25 meters long, 10 meters or 20 meters wide, and you can't see the top of the domain. Maybe I can bring that up here. I'll zoom out a little bit, and this is 40 meters high. So with that, I'd like to go ahead and start the GUI. All right, bring it up here. The GUI is called G3d, which is used for running C3d. So to start, what we're going to do is to create a new project. It'll be a combustion product, and you have a variety of fuels, default fuels, but we're going to pick ethylene in this particular case. And we'll go in and start building the model. These are kind of set up in the way that you would want to enter the data. The time step, or the time, is initially set up to run one time step so that you can see if the problem runs and to get some data without actually going too far. The equations are set up for combustion at the moment, so we don't need to do anything with those particular parameters. One thing I should mention, that the z coordinate is up. All right, so the acceleration of gravity is minus 9.8. Everything is in SI units, so I'll be presenting things in kilograms, meters, seconds, and so on. The first thing you want to do is to get some materials. So the easiest way to do that is to go into the material database, and we'll pick up a couple of them. Just double click on what you want. We'll pick on concrete. We'll get a couple of insulators, and I'll show what those are used for in a moment. And let me see, we want to get the ground's going to be, well, let's just leave it as concrete. All right. Oh, we do need one more material. We need the stack. Let's make that out of steel. That should work. So now we have these materials. We don't want to duplicate the name because the names are important in this particular thing. So what we're going to do is change this to insulator 1 and this one to insulator 2. We'll call this one insulator 0. Okay. Now we could use concrete as it is, their properties. However, this is going to be a 10-second run, so the ground will not heat up very much. So what we're going to do is reduce the specific heat to, let's say, 10, so it heats up quite a bit faster, and you'll actually see some temperature change of the ground. All right, so now we've got enough materials for this particular problem. The default gas is air, and we'll leave that. Okay, now we want to set up some initial fluids for the initial conditions. We have air and ethylene gas, and that's fine for this problem because ethylene is going to be burning in air, and we don't really need to add other gases. So now let's go to the geometry. The default domain is going to be in the x. We're going to have some wind blowing in the x direction. So, and we'll put the stack at 0. So we'll make this a minus 5 meters and stretch it out to 25 meters. The y dimensions we can leave as it is, plus and minus 10. Uh, and for the z dimension, we want to add some ground. So we'll go from minus zero point 0.1. The ground's going to be 0.1 thick. And we'll go up to a height of 40 meters. And it's all going to be air. And that's all we need for the computational domain. The next thing we're going to add is the ground. So we'll add a rectangular region, and it's concrete. So we'll just call it the ground for now. The x dimensions will be minus 5 to 25. I think it was 25, yeah. Minus 10 to 10. And from minus zero point 0.1 to 0, it doesn't go all the way up. And it's going to consist of, so here's where I want to explain why we're going to pick insulators. We'll pick insulator 0. The reason we're going to do that is that we want to track the temperature response of the ground itself. And we want to set up a coordinate system in that ground. And we do that through the use of subgrids, which allows you to resolve the coordinate system. And I'll show how that's done in a little bit. But in order to get a different coordinate system, we need to map it to an insulator and then find that insulator with a subgrid and then remap it with a new set of new coordinate system. And I'll show how that's done in a little bit. The next thing we want to do is to add the stack, and that's going to be a cylinder. We'll call it the stack. The axis is going to be in the z direction. It'll be at 0, 0 for the center of the axis. It's going to start at 0 and be 25 meters high. And the diameter is going to be 1 meter. And we're going to make this out of solid insulator 1. And we're going to map the surface of this cylinder to a steel substrate, again with a finer coordinate system. So this is all we need for the geometry. And now let's put in some boundary conditions. They start out with air and 0 flow. So we're going to add a combined, what we want to do is put in hydrostatic pressure everywhere. So I believe that's a combined boundary condition. No, it's a momentum boundary condition. No, it must be combined. I've got to find it here. There it is, hydrostatic pressure. And if there's inflow, you have to assign a temperature. So we're going to give it 300 Kelvin. And it's going to apply to the entire, to all faces. Okay. And the next thing we want to do is add wind. So for the x minimum boundary, we're going to put in a combined boundary condition, and we're going to use mass flux and temperature. It's a fairly easy one. We'll use a wind speed of 10 meters per second, temperature of 300. And that roughly corresponds to about 20 miles an hour, a little faster. And at the x max boundary, we'll use the same boundary condition. Combined mass flux and temperature, it'll also be 10 meters per second at 300 Kelvin. Okay, so now we have all the boundary conditions we need to run this particular problem, a stack with wind. Now, okay, let's save this. Oops, oh, we got to give it a name. I'm saving the data. We'll go to a test location. Let's go to users, me, test directory, and we'll call it C3d INP. Okay, so the data has been saved. Let's go to mesh again. Delete scan mesh. All right, let's put in 50. Whoops, 50. Okay, so it's going from x-axis from -5 to 25. And I think 7 is a good number, but what we want to do is to use a variable grid length, and we'll use a negative direction power law, which kind of stretches the coordinates in the negative x direction, and it starts from a finer grid, which we're going to put here on this stack. And for the stack, we're going to use 5 cells across it. So the 5, and the average dx will be 0.2 meters. And for the positive x direction, we're going to use a positive direction power law. So it's growing in the positive x direction. And we'll use we'll use 40. So we get some reasonably fine coordinates in the plus x direction. Let's now do the y direction. We'll do the same thing. Right click, delete scan mesh. Okay, we'll put in, say, 40. It wants you to estimate the number. This comes in handy at times. And here we want to stretch them in the negative direction. So I'll put in, say, minus 14. And we want to stretch this in the positive direction. Let's put in 14 again. And we want to use the same number of cells across the stack, so it also has a width of 0.2. Okay, and let's now do the z direction. We want to scan that geometry. Let's put in, say, 40 again. 1 is good for the ground. We don't need to resolve the grid. We're going to do that with a subgrid to resolve that coordinate. From 0 to 25, that'll be the stack. Now, if we want the cells to be variable, we're going to put in a negative direction power law, because we don't really need to resolve much in the negative x direction. So we'll use 12 here. We also want to have it be a positive direction power law in above the stack, but we need something to grow from. So we're going to insert a point to be a 0.2 meters above the stack. So it's going to be 25.2. Whoops, I'm sorry. We're going to call it stack start. And it'll be at 25.2. All right, so now we've got 25 to 25.2. And we're going to put 1 cell there. And let's make this 15. Let's go a little finer than that. Let's go with 20. And it'll be a positive direction power law. Okay, so we've got pretty much all we need. So, okay, let's save this data. And let's run it for one time step so we can see what the mesh looks like. Whoops, it doesn't think we saved it, even though we did. So run it. Okay, so now we're going to view the mesh. And we click on this button, View Mesh, and that brings up Paraview, which will show us the mesh. You can see it's finer around the stack here so that we can resolve the flames. And it's going to be fairly fine around the region of where the gas comes out, so we can resolve that. That looks fairly good because the flames are going to be going up, so we've got a fairly fine grid there, and this grid actually looks quite good, so we're going to keep that. We'll get rid of that. We'll go back, close this. We'll go back and modify it. Now we're going to add the subgrids, And these are going to allow us to resolve the gradients in the ground, the stack, and to also eject gases from the top of the stack. So what we want to do, let's do the ground first. We'll call this ground. And we'll call this ground too. You can have multiple layers. It'll be, let's make it 0.3. This doesn't have to correspond to the 3D grid. We're going to resolve it with, say, 5 cells in the Z direction. And it's going to be, well, we need to give it something for fluid, even though it's not going to have fluid in it. And it's going to be concrete. Now we want to do auto coupling, and I think we want to do the entire domain. And now we want to find the material we want to map it to, and that was insulator 0, which is what we constructed the ground from. So it's going to map this coordinate system to this material in the 3D grid, and it's going to consist of concrete with 5 cells through a depth of 0.3 meters. We need to give it some boundary conditions, and adiabatic no flow is just fine for that. And what that does, it allows it to have thermal radiation. Oh, except there is one problem. The default condition for these materials is an emissivity of 0. So with that, it will not be absorbing any radiation. So I'll go back and add the emissivity of something reasonable for ground in a moment. But let's finish adding these others. And here, let's do the stack. Let's call this the steel wall. Steel wall, let's make it a depth of 5 centimeters. And let's give it 5 cells. So since this is curved, it's going to have to, put, actually you don't need air, but we'll leave that anyway. But you do need air in the other problem. Let's see, we're going to make this out of steel. And we want to do a coupling to material 1. That was what we built the stack from. We don't want to do the entire domain because the ground is also going to be, we want to go from 0 to almost the top of the stack, not the very top. So we'll do 24.9. Okay, so we've got that. So, and now we want to add one more grid, and that will be how we eject the ethylene gas. We're going to call that the stack exit. Let's see, we'll call it exit. It'll be a length. The length is irrelevant in this case, and we're going to use 1 cell because this is only going to be pushing gas out. And it's going to be ejecting this gas, whatever the properties of that gas is. And we want to couple it to the same thing as the other stack that we built it from, which was insulator 1, but we want to look only above and below the top of the stack. If you put in zeros here, it's going to search over the entire domain in those coordinates. So X and Y is fine. It's going to look everywhere. But we want to look just below and just above the stack. So we got 24.9 and 25.1. So it's going to look over the entire horizontal dimensions, but only on this restricted Z-axis. And here is where we put in the boundary condition. Let's see, it'll be a combined, left is corresponding to X min. It'll be a momentum boundary condition, and it'll be, no, not that one, combined. Yes, combined. Mass flux and temperature. So it's going to be ethylene gas, because we told it that was what the gas is, and we're going to inject it at a velocity of 3 kilograms per meter square per second. And let's use 400. Okay. Now it actually uses the conditions of this gas, which were defined earlier. We can go in and check what those conditions are. X max, now it has, this is what's inflowing into this 1D subgrid. X max is what's going to be flowing out, so we have to modify that. And what we're going to use there would be the momentum boundary condition, and we're going to use the 3D pressure. The 3D pressure is the pressure inside the 3D domain. Remember, this is its own separate coordinate system, but it's coupled to the 3D domain through this boundary condition. So it's going to be ethylene gas going through one computational cell, flowing in with this mass flux, and going into the 3D domain. And it does it at this location in the Z location. So we've done that. Okay, now we got to go in and we want to map uh, the radiation properties to these other materials. So we'll go back to properties and let's see, concrete will have an emissivity. Well, let's just give it an emissivity of 1. I don't have time to look it up at the moment. And steel, we'll do the same thing. We'll give that a surface emissivity of 1. Okay, so we're about ready to go. The output is set up to look pretty much in the middle of the grid. That could be modified to add more or less output. Let me put in the VTK is what we're going to get. We use it with ParaView, and the time steps for that are 0.1 second. So every tenth of a second, we're going to get a VTK file, which we can use for animation. So everything is in good shape right now. Okay, we will go in and run it for one time step. Looks like it ran just fine. So let's go and might as well just run it for a long time. Let's go in and modify the time steps. We'll make this 20. Oh, let's make it 10,000. Max time step of 1 millisecond is fine. Let's print every 10 time steps. If you print every time step, you'll get too much. And let's make this 10 seconds for when to stop the calculation. We'll save that. Okay, and now we'll just get it running. Whoops. We'll run. And it should go on. Here it's mapping the 1D subgrid to the top of the stack. So these are the source terms. It looks like it's got that many, one for each computational cell up there. So it looks like it's a sudden onset, so it's having some difficulty getting started. There are some instabilities associated with the high-speed flow. But we should, it looks like to me, it should just start up. The time step is increasing. It'll go up to the max time step of 1 millisecond after a couple of minutes. So I think I'm going to let this thing run for about an hour and then come back and see how it did. So I'll just terminate the video at this point and come back in about an hour. Okay, it's been running for about an hour. I've restarted it, and let's have a look at the output. First thing we'll look at is XPlot. Probably want to view the Y plane in the center, and let's look at the temperature. There you can see the ethylene coming out. It's forming a flame at the top of the flare, as you would expect. Now, I don't know whether I mentioned it or not, but the combustion model is set up so that ignition occurs at room temperature. You don't need to apply a high temperature pilot to get the ignition going. And the reason for doing that is for user convenience. If you want to run an ignition problem, you need to modify the combustion model somewhat to do ignition. But for convenience, we're running it so that it burns at room temperature. So you can see that the flare is coming out and it's flowing out of the zone. And this is a slice right down the center plane. Let's, what else can we look at here? Let's look at the volume fraction of soot. So one of the things that you find whenever you start up a flare is that you get a big blast of soot that comes, and you can see it here. It's flowing out of the system, and then the flame starts to burn the soot quite nicely, and it continues to burn it without much smoke. I think that's all that we need to look at here. So I'm going to press Q to quit, and we'll go in and open ParaView. We use it to view the mesh, but let's go ahead and open ParaView. I've already set up a state file which allows you to save a bunch of settings that you'd set up previously. I called it flame.pvsm. And it was what we looked at earlier at the beginning of the thing. There's the beginning of the flame. Let's rewind it and go ahead and start it up. Here we see the ground warming up as well as the top of the stack. The temperature, it goes up about 30 degrees or so. Similar for the skin of the stack. And let's take a look at the heat fluxes. That would be in this file. That's surface temperature. Here's the heat flux in watts per meter squared. Move the legend down. Rewind to 0. We'll start that up, and you can see the heat flux is kind of this green color. So it's around 5,000 watts per meter squared. It's much higher here at the top of the stack next to the flame. Closer to about 100,000 watts or higher yet even. So it's very hot at the top of the stack. I'm not sure what else we might want to look at. See, oh, this is soot. The soot doesn't come through very clear. For the flame, we're actually viewing water with a mass fraction of 10%. And that seems to work quite well. This is about what the flame would look like. And in this problem, we have a 10 meter per second wind flowing in the positive x direction. And I think that would conclude the tutorial for now. So hopefully that can get new users started.